everyone, to today's Fireside Chat with Google's Flood Forecasting Initiatives lead, Sella Nevo. My name is Stacy Chan. I'm on the Product Partnerships team at Google, and I am thrilled today to be joined by my very esteemed colleague, Sella Nevo, who is the engineering lead for the Flood Forecasting Initiative. We've had the privilege to launch one of my absolute favorite projects at Google, and today I don't want to steal any more of Sella's thunder, but he will be giving an overview of this life-saving technology. So Sella, take it away to introduce the Flood Forecasting Initiative.
So hi everyone. As Stacy mentioned, my name is Sella, and I want to maybe start us off with a concrete example of why we're doing this kind of work. Last year, we visited the Nagawa village in Bihar, India, only a couple of days after the flood that you're seeing on the screen right now. And when we arrived, only a handful of houses were left standing. There was no warning for this flooding event, and while this video was taken during the day, floodwaters originally began to rise at night when most people were sleeping. When some people woke up, it was already too late, and 2 people died that night. And sadly, this story is not an outlier. Floods are the most common and one of the most deadly natural disasters on the planet, every year affecting hundreds of millions of people, causing between thousands and tens of thousands of fatalities and costing around $10 billion in economic damages. But on a brighter note, early warning systems are an incredibly effective tool in mitigating the harms of flooding. According to the World Health Organization and the World Meteorological Organizations, early warning systems can reduce about 40% of fatalities from flooding. And research that we've performed in collaboration with the Yale Economic Growth Center show that that receiving warnings before flooding arrives doubles the likelihood of people evacuating, moving precious belongings, or taking other protective actions. In fact, early warning systems are so cost-effective that in 2019, the World Bank found them to have the highest cost-benefit ratio among the climate adaptation interventions it recommends. And it's for these reasons that we've started the Google Flood Forecasting Initiative. We believe that everyone should have access to forecasts and warnings so they can be safe and informed. But for that to happen, the underlying technology has to be one that is computationally scalable and sustainable enough to span the entire globe. Our current focus is on riverine floods as opposed to flash floods or coastal floods, though eventually we hope to be able to assist with all types of flooding. There's a lot that Google can do to help move the needle in this space. Google can distribute alerts to the billions of people that use its products daily. It can use vast computational resources that we're very happy to utilize for free to improve the accuracy of the models that help flood forecasting systems. But what we believe is going to be our biggest contribution and the biggest thing that Google really brings to the table is our machine learning expertise. We believe that these tools are capable of significantly improving the accuracy, reliability, and scale of flood forecasting systems, and that's a lot of what we're going to be talking about today as well. However, we recognize that we're only here to help. Governments are the ones with the infrastructure and the mandate to take care of the safety of their citizens, and most of the relevant expertise and experience lies in organizations that have been doing this important work since long before Google has even existed. This is why we're engaging with governments, NGOs, the World Bank, and academic institutions to combine our strengths and find genuinely innovative solutions that really help people on the ground. I want to focus on 3 main components, which are the core parts of our efforts. The first is the hydrologic model. We'll then discuss the inundation model, and finally talk about the distribution of warnings and alerts. The hydrologic model is a model that accepts as inputs things like precipitation, soil moisture, solar radiance, and more, and produces a forecast for discharge or water level throughout the river. It is the key component responsible for increasing the lead time of our forecasts, giving people and the authorities more time to prepare for an upcoming flood. Now, the classic approach to these types of models is to model each physical process using a different physics-based model. And in practice, we pretty much never have enough information to actually simulate the full physics, So we use simpler conceptual models to do that job. Now, this methodology has several downsides and limitations. Despite growing and becoming pretty complex in general, they are still incredibly simplistic relative to the actual physical processes that they're trying to model. They're also often over-parameterized, which means that these models can start perfectly matching all of the historical data that we have, but still not matching future events that have yet to happen. And then finally, they require continuous manual calibration by experts, leading them to be expensive and not scalable. Because of these reasons, in the past few years, we've been taking an extremely different approach. LSTMs are an architecture that allows neural networks to model time series. What's really interesting about this type of modeling, though, is that we do no explicit modeling. The model learns on its own the full relationship between the inputs it receives, such as precipitation, and the outputs it needs to produce, such as discharge. And we've been able to show that these LSTM-based models can achieve significantly better results than classical models. What we're seeing here is the result of such a benchmarking process comparing these different models. Each line represents a different classical hydrologic model. And technically, what this graph shows is the cumulative distribution function of the Nash-Sutcliffe efficiency score of different models across hundreds of basins throughout the United States. But really, the only thing that you need to know about this graph is that the lower each line is, the better that model is doing. It's getting better scores on more sites. Now, here you can see the performance of our LSTM-based architectures. Now, in addition to providing better accuracy, there are two additional advantages to these models that can't be seen from this graph. The first is scale. While classical models require many hours of work for each one of the hundreds of basins that they're trained on, the LSTM-based model needs to be trained once and applies across the whole region. The second is generalization. The comparison you're seeing on the screen now is actually not a fair comparison. The classical models have been allowed to calibrate based on the specific basin they're forecasting for. However, our LSTM-based model has had the site that it's being tested on hidden from it, and in fact has never seen data from the site it's being evaluated on. So the LSTM performance you're seeing is actually its performance on what's called ungauged basin, though still within the same region of other sites that it has seen. We're continuing to improve these architectures. Recently, we've been working on creating models that can communicate information to downstream sites more effectively, as well as combine transfer learning between sites with the per-site specialization. But while it's always fun to talk about the academic breakthroughs, it's no less important to tackle the practical issues that are inherent to real-world data and operational systems. We've done a lot of work on reducing data latency, detecting and correcting errors in data collection, and increasing the speed and frequency at which these models are run. This work is often less appreciated, but critically important to take these models out of academia and allow them to create actual change on the ground. So we've deep dived for a bit on the hydrologic model. Now let's move on to the second component of an actionable flood forecasting system, the inundation model. Inundation models simulate the water's behavior across the floodplain, like you're seeing on the screen right now. This means we can identify in advance who needs to be warned of danger, as well as where they can go to be safe. There are a lot of challenges to scaling high-quality inundation models globally. The first is the lack of globally available elevation maps. In most of the world, elevation maps are at too low a resolution to run effective inundation models. Here you can see one example of this. On the right, you're seeing a simulation of a river. This one is specifically close to Hyderabad in India. On the left, you're actually seeing a simulation of the same river with the same amount of water, but using an SRTM-based elevation map, which is a 90-meter resolution. As you can see, it's really hard from the simulation on the left to know not only who's going to be affected, but even when the river is overflowing at all. Another challenge is stainless. Even if you do invest in a really high-quality elevation map, 2 or 3 years afterwards, many rivers will have moved to an extent due to river erosion and other processes. And as a result, these things become not usable for these purposes relatively quickly, at least in kind of very dynamic rivers. Because our standard methodology currently requires specialized hardware, either on satellite missions or on airplanes and so on, having information that is both high quality and accurate, but also not stale, becomes a challenge. So one way, for example, that people produce these maps is through stereographic satellite imagery. You send out a satellite with 2 cameras aimed at the same location, taking pictures at the same time, but with slightly different angles. And based on those differences, you try to understand what's going on, but it's hard to do this at global scale frequently. That's why we're taking a slightly different approach. Instead of using expensive, specialized satellite missions, we purchase large amounts of high-resolution optical imagery that is captured anyway, every day across the globe. These are completely standard optical images, the kind you're used to seeing on Google Earth and elsewhere. We then use a process that is somewhat similar to the stereographic imaging I described earlier. We continue to use the differences between the images to deduce the height of the ground. But because we're not using specialized missions, but rather arbitrary images, we have to work a lot harder on the software side. We need to incorporate images from different sensors with different types of optical distortions, with major changes between when the different images were taken, and with no one planning the angles of these images to make our job easier. But the upside is that once we've done that work, this allows us to generate 1 meter resolution images anywhere in the world and update them annually. This allows us to utilize images like you see on the right instead of kind of the standard globally available images like you see on the left. Once we have these maps, we need to actually simulate the water flow. The classic way of doing this is what's called a finite difference solution to the Saint-Venant equations. We've implemented our own version of these solvers in a way that can be distributed across Google's supercomputers. But as much as solving differential equations can be fun, there are still major challenges to deploying these models or even running these models at scale. The first is computational costs. As we span globally, running these things becomes challenging. Due to how these models work, every time we want to double our resolution, the number of processors that we need multiplies by 8. Since we now have maps that are 90 times the resolution, this means about 700,000 times more computation required, which can be a challenge even for Google. To help address this, we've re-implemented these models on specialized hardware called TPUs. TPUs were originally optimized for machine learning uses, but with 420 trillion operations per second and 128 gigabytes of high bandwidth memory, they come in pretty handy for solving differential equations as well. As a result, our TPU implementation is 85 times faster than the CPU implementation per each core. But this still isn't enough to reliably run these models at global scales. Here we can see an example of one of the first alerts we ever sent out. This one is for Patna, India. What we're seeing here is a comparison between the areas we alerted and the areas that ended up being flooded. The blue areas are areas that were indeed flooded and received an alert. That's good. The purple areas are areas that received an alert but did not end up being flooded. In this case, we wanted to warn people who were close to flooding as well, and so we felt comfortable with the purple buffer surrounding the flood. Finally, the red areas are areas that were flooded but did not receive any alerting. As you can see, in most of the map, we have very few red areas, which is great, except for that pretty big red blob at the top. For months, we couldn't understand what's going on there. There's a huge embankment between the river and the field that you're seeing in red now, and it just doesn't make physical sense for water to be able to overcome that embankment. And after being frustrated for months, we ended up flying out to Patna to talk to some of the locals and understand what's going on the ground. And what we found out is that when farmers want to hydrate their fields, they simply dig a hole in the embankment so that the water can easily go through. And of course, there's no way for us to see this from the satellite data we have access to. And we don't want to manually need to identify and fix these areas in every region across the world. However, we do see, based on our satellite data, that these places consistently get flooded. So we started asking ourselves, why can't we have our models learn this automatically? We set out to try and build a model that can automatically learn from its mistakes and kind of fill in the information gaps for the things that it doesn't know. This includes not only the example that I just mentioned, but also things like the riverbed bathymetry, what goes on underneath the water, which we can't know based on optical imagery and is often unknown in many rivers around the world. To do this, we've set up a pure machine learning model that learns the relationship between the gauge measurements that we receive and the flooding behavior on the ground. This model doesn't depend on high-resolution elevation maps at all. It allows us to automatically learn from mistakes of the past. Of course, this model has its downsides too. If there are major changes to the floodplain, this model doesn't know how to adapt naturally if it hasn't seen examples before. And such machine learning models often struggle to generalize beyond the range of their original training data. So we've set out to improve this model further. This has led us to look for a solution that incorporates both what we do know about the physics and what we don't know about the bathymetry, floodplain, and more. To help address this issue, we've developed the morphological model. This model learns the one-dimensional river profile using machine learning, and then expands that river profile into the full two-dimensional inundation map across the floodplain using physical principles. This allows us to automatically fix many of the problems that pure physics-based models have, while utilizing elevation maps and physics to correctly generalize to unprecedented events and other events that are challenging to forecast. All of this allows us to produce inundation maps that are fairly accurate down to a resolution of tens of meters at unprecedented scales. Of course, for those for whom this matters the most, our results look more like this. While we were visiting affected regions in India, we did what we don't recommend other people do, and we looked at where our alert said flooding should begin and drove all the way to the flood. What we found is what you're seeing here on the screen, where standing on the line of where our forecast said flooding should start is indeed where we saw water beginning. But of course, none of this work is useful if we don't make sure that this information reaches the right people at the right time. We have several strategies to making sure that that happens. First, we use Google's public alerts infrastructure. This system allows sending millions of people emergency alerts within minutes, engaging with them in different ways. We provide people with local and actionable information on search. We show interactive maps of ongoing and forecasted flooding on Google Maps. And we notify people of flooding near them through smartphone notifications. We also support multiple local languages. We allow you to easily focus on your local area and others around you. And we provide safety tips and recommendations from the official disaster management authority in your country. We also collaborate with the relevant government agencies to make sure they have this information and can act on it. Governments have both the mandate and the resources to create real change and help people in real time. They help in the short term via mitigation and relief efforts, and in the long term through critical infrastructure work, such as building dams and embankments. Now, these techniques are not only more accurate, but really allow us to reach many people who could not have access to this kind of information before. They allowed us to go from covering about 1 million people in North India in 2018 to about 10 million people in 2019 to 240 million people in 2020. Just these past few months, we've sent warnings to about 10 million people directly on their mobile devices, in addition to sharing that information with the authorities and with NGOs like the Red Cross and Red Crescent Federation to support community-based alerting. If you're interested, you can see an aggregation of all of our live alerts at this address, g.co/flood alerts. Though I will warn you that at this point in time, there's not that much going on the dashboard since the monsoon season is mostly over in most areas that we cover. To conclude, our vision is to create accurate hydrologic models that give people days of lead time to prepare. Combine that with actionable inundation models that are spatially accurate, so they know exactly what they should do to be safe. And then use fast warning distribution systems with high penetration, and to scale all three of these globally so that anyone affected by floods will have the information they need to stay safe and informed, no matter who they are and where they are in the world. So thank you all for listening, and back to you, Stacy.
Thank you so much, Sella. I can't compete with a cute micro pig in boots, but I do think we have some very interesting questions from the audience. Sella, the results in the past 2 years from the Flood Forecasting Initiative are astounding and so impressive with how many millions of people you've been able to reach. Floods clearly are a very negatively impacting natural disaster, but I'm curious to know how you and your team decided that a flood forecasting system would have the biggest impact, and what was that thought process for you and your team?
Yeah, that's an important question, and one that we take very seriously. There's really a lot to do, as I think as 2010 or 20 has made even clearer than usual. And despite the fact that Google has a lot of resources, it's the human condition that we have only a limited set of resources. So we really do want to make sure that we prioritize correctly and do things that make a meaningful change in as many people's lives as we can. Now, I mentioned briefly some of the things that we look into, and we originally looked into, and we tried to decide what project to work on. We originally started with about 60 potential interventions that relate to natural disasters, terror attacks, car accidents. We kind of took a pretty wide view, and we tried to estimate how many people we'd help, how significant that help would be, what is the chance that we'll be able to make a significant difference, and most importantly, we tried to see where Google would have a unique contribution. And I mentioned in terms of impact, the things that really drove us to this problem, whether that's the hundreds of millions of people affected every year and the really incredible effectiveness of flood forecasting systems. But we also believe that this has had a unique opportunity to create enormous change in the field, because many, for example, hydrologic models really have had only incremental changes since the 70s. And we really think that there's enormous improvements that can be made to these systems that have real effects on people's lives.
Well, that certainly is a great and awesome responsibility that you and the Google team have to be able to impact hundreds of millions of people, as you mentioned, in that floods really are one of the most devastating natural disasters. And so with Google's mission to try to build for and help as many people around the world who are affected by these floods, Sella, how do you and your team balance the scaling of the Flood Forecasting Initiative and all the AI technologies with still maintaining that precision and hyperlocal relevance to people who are on the ground impacted by floods?
Yeah, that's a great question, and it's a huge challenge. I think it's one of our biggest challenges, trying to combine these two, because the world already has global forecasting systems. GLOFAST is a great example of that. The world also already has really high quality flood forecasting systems that are extremely high precision and accuracy, but at kind of local scales. And trying to do both of those at the same time is really a big challenge. This is something that we're still working on, right? So we're still both scaling up and trying to improve how much we're locally relevant and how much we can convey the information to people in a way that they will understand and will be useful and meaningful to them. But I think broadly our approach is, first, we do a lot to localize. So we started small. We started with one city. We've done a lot of work to try and kind of optimize the way we communicate with people so that they can understand and find it useful. I mentioned our work on local languages. We kind of communicate with local governments to understand what information they can provide, what are their priorities, and we try to put all of our information in a local context. And then as we try to scale up, we try to either automate or at least kind of increase the efficiency of that localization process, right? So instead of trying to, automation doesn't have to mean a one-size-fits-all. We try to make it so that the localization process that people need can be easier to do, whether that's automatically identifying where the user is and then showing them relevant points of interest, things that will be meaningful to them, whether that's making the process for incorporating information about, let's say, local shelters or governmental guidance easier for local governments to share and distribute, right? So making it easier for those local things to reach as many people as possible. And I think that's really critical to make sure that on the one hand, we give people the best information that they really need and not one kind of one-size-fits-all information that might not always be good. But on the other hand, make sure that we don't make it such a boutique product that most people and the people who need it most can't access it.
Sella, the improvements to the localization and even the precision and accuracy technologies are incredibly impressive. But the reality is, as you mentioned, referring to computational costs as an example, there are still a lot of challenges with this kind of technology. Are there others that you see as the biggest hurdles, and what are you and your team doing to address some of technology's current limitations?
Yeah, so there are still a lot of challenges that we're trying to tackle, and a lot of other academic institutions and governmental institutions are trying to tackle as well. I think a few that are kind of top of mind for me. One is trying to address more and more challenging hydrologic conditions. This could be smaller, flashier rivers, and of course, eventually flash floods as well, which I think are kind of one of the points of focus globally in the recent decade. Another is how to take into account what is often unpredictable human behavior. Right? You'll often have spontaneous decisions about what to do with dams or sluices or other kind of human influence on basins, and these are of course incredibly important and will often prevent a lot of harm, but they can make it really challenging to do the forecasting task. And so that is something that we're working on, and I know a lot of people are working on as well. And then finally, we've touched about this a bit, but I think there are still remaining challenges on conveying the information. So while there's a lot of research showing that people knowing about flooding in advance can be incredibly effective, there's also a lot of studies showing that most existing flood forecasting systems convey the information in ways that people struggle to understand. People can often struggle with understanding uncertainty and a range of different options, as well as understanding maps, as well as even understanding things like when you try to convey depth, conveying it in ways that are intuitive to people so that they, not just kind of hard numbers that people don't always understand. We've been doing a lot of work on this, and we have a good infrastructure to be able to iterate and improve these learning. We can do things like A/B testing and see what people understand better and respond to better. But a lot of that work still remains. We're still not sure what is the best way to convey complex forecasts to the people on the ground who need to understand them.
Thank you so much, Sella. Your talk has been really, really astounding and truly inspiring. And based off all the questions that are coming in from the audience, people are chomping at the bit to understand how they can work with you and your team and build future collaborations together. As one final closing thought for the audience, what would you say is the best way to partner with Google on future efforts in this space?
Yes, I think at the moment, we're actively looking at both how we can improve our models and how we can utilize them in operational systems in more countries. So I think the top way to collaborate with us is if anyone is interested in deploying such a system in your own country or in countries that you work with, then please reach out to us. We're very happy to look at additional collaborations and who else can use these systems. And secondly, if you're interested in a research collaboration, if you also have something to contribute and think that our strengths can kind of combine and we can create better forecasting systems for everyone, we'd love to hear from you and work with you. So I think that would be the first step.
Great, thank you so much, Sella. And thank you to everyone tuning in. You heard it directly from Sella. He and his team at Google are very much interested in collaboration. 2020 has certainly been a year of many, many disasters. With climate change, a lot of these incidents, unfortunately, are only going to be exacerbated. So this type of effort only succeeds as we as an ecosystem collaborate. So we look forward to all working together across government agencies, nonprofits, and other technology companies. So thank you so much for joining this Fireside Chat with Sella Nevo, and we hope you enjoy the rest of the Understanding Risk Conference.